In connection with the continuous time implementations of the solvers of what would in that case be differential equations, there is one alternative implementation that can be spoken of. This alternative implementation is significant only for the context of the continuous time case, because for the the discrete time case there is no problem implementing it using delay blocks of the in the manner that we have shown. For the continuous time case, however, there is a practical problem that arises, and that practical problem is simply that whenever you differentiate a continuous time signal which is corrupted even slightly by noise, then the noise tends to get amplified under differentiation. So, repeated differentiation of a signal can be suicidal. It increases the noise level in the signal to greater and greater extents and reduces the performance of the entire differential equation solving system. The solution to that is to see if instead of differentiating we can carry out a series of integrations. Now, this clearly must still solve the same equation. That is a requirement that cannot be relinquished. The advantage of using an integrator is that instead of amplifying the noise the way a differentiation does, the integration actually averages out minor fluctuations. Thus, let us see if we can take the original differential equation and implement it using integrators instead of differentiators. The original equation, of course, only consisted of a set of terms on the left side starting from k equals 0 to n a k and on the right side conventionally we just had a forcing function, but in our more modern, more generalized formulation we allow also derivatives of the forcing function to exist, so that we actually write it in this form. Right. So, this is our general formulation. Just as I said for the case of the discrete time version of this problem, the solution of difference equations, the derivatives on the right side, as was the case with the differences on the right side, do not in any way make the problem more complex. Since x t is a forcing function, is an input function, its form is completely known. So, computing its derivatives is extremely straightforward. There is no challenge in it at all. In fact, the entire equation we have written here could just together be returned to the previous form by writing this entire function as some x dash of t, where dash of course does not represent differentiation, but just some other signal. And now with this form it would revert to exactly the same approach that we followed earlier for the solution of differential equations. But this is worth retaining, so let us do it. All right. Now, suppose we have, as shown here, n derivatives, a linear sum of n derivatives of the solution adding up to be equal to a linear sum with different coefficients b of n derivatives of the input. We want to solve this without actually using derivatives. If this is the constraint we put upon ourselves, how do we do it? We do it by recognizing that repeated integration will cancel out the differentiation. So, if we integrate this entire equation on both sides capital N times, what do we get? the equation now changes to, now having integrated n times, what we will get is the nth derivative of y t will now become just y t, because the n differentiations have been cancelled by n integrations, and the lowest derivative of y t, namely a naught y t, this is the last term on the left side for k equal to 0, that will now become the nth integral of y t, the integral of y t versus against time n times. We need a notation for this, because writing it with the integral notation becomes extremely clumsy. So, we will just write this in the following manner. Let us say that the 0th the integration of y t with itself is written as y t itself equal to y 0 of t. The first integral would be integral minus infinity to t dash to t, okay, y t dash dt dash is what I will call y 1 of t. This is the first integral, first running integral of y t against t. Now, we only need to generalize this and say that integral minus infinity to t of y k of t dash against t dash is what we denote by y k plus 1 of t. So, this is the notation we will use. Okay, with this notation, let us see what happens. We can rewrite that equation, or rather the equation that arises after n integrations would look like this. The left side would take the form the left side would assume the form a 0 y k of t plus a 1 y k minus 1 of t plus so on up to a n y 0 of t, the last term being equal to a n of y t. Similarly, on the right side, you would get b 0 x k of t plus b 1 x k minus 1 of t plus so on up to b n x 0 of t, where the last term again is just equal to x t. Now, let us write this in using the sigma notation to see what we get. This would be equal to saying summation k equals 0 to n ak y n minus k of t equals a similar expression on the right side. This is what we would get. Thus, to obtain successive members of this sequence on the left side, sequence of terms on the left side or on the right side, we need what we will call an integrator block in place of a differentiator block. In short, what we would require is a block that does the following, a block that we have already introduced. You apply to it a function like x t, and what you get over here is x 1 t. This is what you should get on the right side. This is a block that we will have this symbol inside to identify this nature of this block. Now, with this kind of a block, can we do something? Can we construct an expression for this? Yes, we can. Let us see how we do that. We need to isolate the term corresponding to y t, because that is the solution, that is what we want. So, how do we do that? The coefficient of y t was a n. So, you have a n y t equals the entire expression on the left side, that is k equals 0 to n b k x n minus k of t minus k equals 0 to n minus 1 a k n minus k of t. Thus, now the highest integral on the right side, the lowest integral on the right side would be n y to the n minus 1, that is y 1 of t, because y 0 of t is out here on the left side. So, this is what we want to implement. Of course, after making the change that we take away this a n coefficient over here that I am pointing out to right now, and place it over here on the right side. Fine. In order to do that, we simply erase this here and write instead one by a n on the right side, and enclose the rest of the expression in brackets. So, this is the expression we want to evaluate. The way we proceed with it is not unique. We could do it using direct form 1, we could develop it using direct form 2, but since we already know direct form 2, we probably need not indulge in using direct form 1 with its more expensive manner of doing things. So, all we need to do now is to see how to build this system. We will assume that, as usual, we have y t available to us. So, let us say that this is y t. yt, which is equal to y0 of t. What do we need? We also need the successive integrals of yt. We also need the successive derivative integrals of xt. And if you recall how we did it last time, then we will recognize that the coefficients of xt all appeared on the right side, the coefficients of yt all appeared on the left side. Or if that is too much effort, let us initially develop the system using our conventional direct form 1 implementation and then make the required alteration. So, let us go back to direct form 1. Alright. So, I have yt, I need successive integrals of yt. So, I do this and then I go on like this until I have the last integrator, at which point I get I get yn minus 1 of t. Fine. Now, I have to use all these. The coefficient of yn minus 1 will be a1. So, this has to be multiplied by minus a1 minus a1, then the previous term has to be multiplied by minus a2 and so on until this one is multiplied by minus a n minus 1. What you would see here obviously is a n to the minus 1, right. This would give me yt if I already had the rest of the terms, but this has to be added to several other things. In fact, this will not come right here, this will come a little later. Let us first generate the rest of the part. We have to add all these terms now. Let us add them. This is a sum that we are generating. This should also be appended to all the terms arising out of x. So, we start with xt and have a series of integrals of xt as follows. First integral and so on until the nth integral, so that here this is xt over here and here we will have xn of t. Xn of t has to be multiplied by b0, xn minus 1 t has to be multiplied by b1, these two have to be added and so on until here you have b n minus 1 t as the scaling coefficient, and this gets added to all the terms met along the way, and finally you have here b n and this gets added to all the things that have come in from before, and this whole thing gets added over here. Now, at this sum you have practically everything that should equal to yt except for the scale factor. and that scale factor as we know is 1 by a to the n or a to the n to the minus 1, a n to the minus 1. This gives us the direct form 1 implementation. If you want the direct form 2 implementation, you know how to go about it. We do not have to summarize that thing here, you just have to literally replace this block over here to the right side. Let me just call this, for simplicity, let me just call this say H1, and let me call this block H2. So, the system we have now is we have xt going into H1, this going into H2, and this finally yielding Yt. The direct form 2 implementation would be just to take xt, pass it to H2 first, and then pass it to H1, and then getting Yt out of it, with of course the also implementing the savings that you get by collapsing parallel sets of integrators into a single set of integrators, into a single sequence of integrators. That is all you need to do to get this direct form 2 implementation of the same system. There is one question that needs still to be asked. You see, suppose we go back to the direct form 2 implementation for the discrete case of an nth order difference equation. For the nth order difference equation, we had a series of delays going down like this. And on the right side, we had B1, B0 and so on until we had Bn. On the left side, we had minus A1 on to minus A n, and we had a lot of summations. On the left side, similarly, we had x n, y n coming out of here, and finally 1 by A 0 or A 0 inverse being the term over here. This is what we had. This was the direct form implementation 2 of an nth order difference equation solver. Where do the initial conditions or the auxiliary conditions go? Suppose we ask this question. We now have to qualify what we did and all the things we said about the auxiliary conditions. In a theoretical level, at a theoretical level, I said that if you have a difference equation or a differential equation of nth order, you will have an infinite number of solutions, and in order to pick a particular solution out of the infinite number of solutions, you simply had to specify a set of auxiliary conditions. I further said that those auxiliary conditions could be specified at arbitrarily chosen instants of time, not necessarily the starting instants. But it does make a difference when you are implementing a causal system. Whatever you build using a circuit like this that you see on the board right now is always a causal system. As I said, the anti-causal system looks good on paper, but it cannot be implemented because in a physical system things are forced to be causal. Now, when things are forced to be causal, what happens to the specification of auxiliary conditions? The simple answer is the following. Let me illustrate what I mean to say by drawing the series of curves that represented the capacitor's charging curve for the case of the first order differential equation. We had a series of curves going like this, and we had to pick one of them. As I said, in order to pick one of them, we could specify the initial condition on the y axis, that is to say the voltage axis, at t equal to 0, that is to say, or as I said, we could specify it at any chosen instant of time over here. The problem that I now introduce to you is the following. If you choose an arbitrary instant of time such as this, that means that time is still in the future when this curve has to be drawn at t equal to 0. Let us call this time t1. t1 is greater than 0. Now, if you want to solve the differential equation and get a unique solution, a unique curve that represents the solution, then that curve should be drawn from t equal to 0 to t equal to infinity. That means the solution must be obtained from t equal to 0 to t equal to infinity. Let us say this is obviously what we require. Now, mathematically it is all very nice to say that the value of Vc of t1 must be equal to V1. That is a perfectly valid auxiliary condition inasmuch as it identifies a specific curve out of the set of all possible curves that could have served to solve the differential equation. But before t1, that is to say during 0 less than t less than t1, the system that we actually manufacture and place on the table must be able to tell us what is Vc of t. Since we are going to specify the condition only at t1, the system still does not know what you are going to specify as V1. It does not know the value of V1. Therefore, it is not possible for the system to anticipate the value of V1 and generate the curve accordingly, because V1 is still in the future. V1, which is Vc at t1, is still in the future. Hence, for a causal implementation of a difference equation or differential equation solver, the auxiliary condition necessarily has to be the initial condition. All right. This takes nothing away from the arguments we proposed at that time. They were not wrong, they were perfectly right. It is simply the fact that in a causal implementation, it becomes necessary to specify the auxiliary condition right at the beginning, so that the correct curve can be chosen out of the possible curves and developed over time until t equal to infinity. This does not negate anything that was said before. In fact, I can say things the other way around for an anti-causal system. For an anti-causal system, being solved from t equal to minus or rather t tending to minus infinity to t equal to 0, an anti-causal system cannot look at the past, it can only look at the future. Just like a causal system cannot look at the future, it can only look at the past. It only knows the past, it does not know the future. An anti-causal system only knows the future, it does not know the past. For such an anti-causal system, the opposite constraint would hold. That is to say, the auxiliary condition has necessarily to be a final condition. In this case, the final instant is t equal to 0. So, you still have to specify, y at t equal to 0, because if you specify anything before it, suppose you specify y at t1 less than 0, then the system can be solved by the anti-causal system can solve and give you the output until t1, but after t1 the auxiliary condition has moved to the past of the present and it cannot see the past, it can only see the future. So, if you want the auxiliary condition to be always accessible to the system, it has to be solved, it has to be specified for the final instant, that is t equal to 0. So, these are important remarks that relate the specification of auxiliary conditions to the causality or non-causality of a system. So, going back to this block diagram, why did I draw this? Very simple. You have all these delay blocks over here. Suppose this is a causal system that I am trying to implement, and I want to understand what happens, what are the values of the system at n equal to 0. At n equal to 0, let me just erase this part, now that we are done. At n equal to 0, these amplifiers do not take any time to compute. What will we get as y n? Let us just take a look. We have x 0 being applied over here. I want to see what will y 0 be. Y 0 at n equal to 0, that is to say, will be affected by whatever we are applying over here, as well as the sum of the scaled values of the delayed signal. Suppose we say x n equals 0 for n less than 0. Suppose we say this. Okay. Also, we say that all initial conditions are 0. That is, these values, after all, if this is y n, these are the earlier values we have over here. We also say that y n minus k equals 0 for k greater than 0. Suppose we say this, then the delays over here, all of them have 0 at their outputs, and there is no contribution through any of the summing points, so that the only thing that you get at y 0 equals b 0 by a 0 times x 0. Okay. Now that we have this, we will see what happens at y 1. Sorry. Now let us see what happens for y to y 1. You have x 1 over here. At this point we had x 0 by b 0 1 instant ago. That is, at n equal to 0, this was x 0 divided by a 0, not b 0, y 0, x 0 by a naught. X 0 by a naught is now available at this point. X 0 by a naught is the quantity that gets multiplied by b 1 on one side and by minus a 1 on the other side, and gets added to x 1. So, y 1 will be equal to x 1 plus x 0 by a naught multiplied by minus a 1, that is one side of it. That is what we have over here, and this gets now scaled by this quantity b 0 and then gets added to x 0 by a 0 multiplied by b 1. This then is y naught, or rather y 1. This is the value of y 1. It has incorporated the value of x 1, it has incorporated the delayed functions that have arisen in the meantime. Now clearly you can see y 1 uses both x 1 and x 0, fine. Y 2 will use x 1, x 0 and x 2 and so on, so that after n instance, where n is the order of the system, the past n values of x will come into the picture, and even older values will come into the picture because of the autoregressive nature of these blocks on the left side, and the system completely starts functioning as it is supposed to. But in the initial states, because we chose all the delay outputs to be equal to 0, the system has developed in this fashion. On the other hand, we could have set some initial conditions. We could have said that y minus 1 is equal to this, y minus 2 equals this, y minus 3 equal to this. And if we look at the direct form 1 implementation, then we can clearly see how that system would take values of y minus 1, y minus 2 and so on as initial conditions and use them to contribute to the output right from y 0 to y 1 and so on. Alright. So, this more or less closes our discussion of differential equations and their solutions. It has been a long discussion, gone into several hours. At this point of time, we will close this discussion because it has been sufficiently thorough, and we will now proceed to discuss a totally different issue.